manufacturing process lah. So I will guide you regarding this topic. I believe you already used CAD system during your first year. Okay. Okay. So why we need CAD CAM system? Okay, I don't know. Do you have any experience using manual drawing or not? But during my time, this is how we draw. Okay, this is how we draw engineering drawing using T-square, big huge board, and it's very difficult and lengthy process. At that time, we don't have any computer available like now. Even though there is a computer back then, but maybe it very expensive and difficult to buy and to get lah. Software not compared to today lah. Everything is available. Some of them are open source, free. You can use it online. Draw it online, whatever you want. Okay, so this is CAD, computer aided design. Okay, so why this is good? Because using this software, we can simulate our design, right? So for example, if you have design like this, remote control car, okay, you what call it? You draw it, you have some colors, okay, assign some colors, you assemble it. You need to assemble it, and then you can even, I think, play it. For example, this one animation. You can have animation, the gear, how it works, the tire, what will happen in the software lah. So we have many CAD software, SolidWorks. In manufacturing lab, we have Unigraphics, UG, okay, NX from Siemens and others. Okay. All right, this is CAD CAM. What is CAD CAM? I think I already know about this. You can read it by yourself. We already discussed about this. So this is the figures, right? The typical figures. Okay, so we have two stage here. First is the design stage. Okay, first is the design stage process and manufacturing stage process. Okay, so before you need to design. Okay, before you need to design anything, you need to know what is the needs lah. What is the needs of the product? Okay, then you have the spec definition and requirement. What you need for the product to make the product. Okay. Maybe collecting some data, some surveys, collecting some surveys and others. Then you design it into CAD process. So in this gray box are CAD process. Okay, you have a conceptual design. Okay, draft it first. Okay, draft it. Then model it, start model it and simulate it in CAD software. Do some analysis, optimize. If you have any problem here, then you optimize it. Okay. Then evaluation. Maybe this one you go back to the survey that you made. Ask them to evaluate your design. Okay. How is this design? Can you give some idea in order to improve it, for example? So they will give some input in order to evaluate the design. Then you have some documentation and communication, okay, before you send it to the CAM process. So in CAM process, you design how to manufacture it. Okay, this CAM process, they helps you to ease you for manufacturing processes. For example, production planning, how many machine you want to use, what cutting tool you want to use. Okay, what tools that you need to have, what different tools, what the size, okay, in order to order material and others, even the programming itself, how to do programming. Okay, then go for production, quality control and packaging before you ship it and market it, marketing. All right, so this is the important product life cycle. Okay. Okay, so this all their description. that we already discussed. Yes, if you have CAD, of course you need a computer graphic concepts. You have a geometrical modeling, and you have a design tool. So this one together, you have a complete CAD tools. Similarly, for CAM, you need to have CAD as the input. You have to have networking. Networking concept means this CAM tools can communicate with machine, for example, okay, and other manufacturing tools lah. For example, graphic tools and etc. So if you can combine all this together, you can have a CAD CAM tools. Then you can also have automation. So automation means you need less worker, so everything is automated, right? So this is the advantage of it. Okay, of course, the main purpose is want to reduce the lead time. So lead time means you want to increase the productivity and have the lesser time working on some design from design stage until selling stage. Okay, so this what called a lead time. When you have the design until the product is finished to go for shop, for example, to send for the sell it. So this one is called lead time. So you want to reduce this lead times. So reduce inventories, okay, increase productivities, of course, improve customer service, improve quality, improve communication and everything. Okay, so this topic we want to focus on focus on NC. Okay, you have to create this NC code or GNM code. So you have a design how the machine will process it, will machine it. For example, if you can see here from my screen, these tools are moving. So how to make this tool moving according to your design, okay? How to cut the metal according to your design. So at the end of this topic or of this class, you will get the knowledge how to make or how to write an NC code. Okay, NC code. So NC code usually is a language where universally used. Okay, for example, we have another language. For example, the way that we talk in communication, we have English language, we have Malay language. The most what do you call it? Commonly used language are English, so that people like now we have in class foreign people, so they can understand it. For example, if I speak Malay, maybe some people are not understand, but NC is a standard language where you can use widely used in everywhere around the world. For example, if I want to machine this kind of product, I write the program and it can be used in other machine made from German, made from Korea. If I send to Korea or if I send it to Japan, they can use the same language, the same coding to produce the product. Okay. So the machine will understand it. Okay, it's not like our language lah. If we change Malay, we change Chinese, or for example, some people will not understand it. So this NC is a standard where all machine will understand it. Okay, this is from previous. Okay, this is a history of NC coding. So you have a program instruction here. Okay, then you have a machine tool unit. So machine tool, a machine control unit. If you go to our lab, you can see a machine. So huge machine, and there is a PC, industrial PC. So this PC is the control unit. Okay, a monitor here. So this monitor is the brain lah, or the control unit. And of course, you have to have the machine tool. Machine tool is the cutting tools here, cutting tools and your product. Okay. and of course a set of instruction. So you have to give instruction to this computer or the control unit in order them to give or to react to your instruction or to follow to your instruction in order to cut the product or to shape the product. Okay, this is the example. Okay, this is the example of a major phase in CNC program. So you have to write this program. Okay, there will be one quiz. Okay, one quiz, 5% quiz for this. All right. So individual quiz. So you will have the design and you have to come up with this coding. So this typical coding are divided into three phases. So you have a program set up in this green color. This one is the removal process where the cutting tool moves. So this is all is the coordinates, Z axis, X axis, Y axis. We will learn how to write it later. And this is the system shutdown. For example, M05 is stop the spindle and M30 is stop all the program, for example. Okay, we will go through one by one the meaning of this M and G. Okay, sometimes people call this NC code, sometimes people call this G and M code. Okay, G and M code or NC code, NC code, numerical control code. Okay, so you will get like this for your quizzes. Okay, similarly like this, you will get the holes, okay, the slots with the dimension, right? So you have to write all these dimension from a datum. So for example, here is the datum, means 0, 0 position datum, a reference point. So for example, 0.75, Y is 1. So Z is, for example, the depth of cut, the depth of the hole. Okay, this one will be instructed in the what you call question. Okay, so here is you can see all the holes with 0.4 depth. Why negative? Because the upper of this is 0 lah. So we negative shows it goes down. The tool go down, right? Okay, so CNC code. All right. So what is meaning by G codes and M codes? Okay. So G codes known as a preparatory function, which involve actual move of the cutting tool. For example, rapid move, feed move, okay, radial move, dwell, roughing, profiling. So all the function of moving the cutting tool, moving the tools, cutting tools. We use G code. Whereas the M codes are miscellaneous function. For example, spindle on, spindle off, tool change, coolant on, coolant off, program stop. So other function, in short, other function other than moving the tools are M codes. You will use M codes. Okay. For example, you want to use what do you call it? Coolant. Coolant are used for cooling the process because in machining, the process will be high heat, so we don't want to the tool warm so fast. Okay, so we use coolant, so it can help to cool down and helps longer the tool life. Okay, so you can tell them machine to on the tools, on the coolant or off the coolant by using M codes. Okay, so this is an example, some of the G code and M codes. So for example, for drilling, you have to insert G81, for example, right? And others lah. For example, you want to change the tool. You have to use M06. Okay, M06 is standard to change the tool. So it follows with TXX. TXX means some machine they have maybe 10 tools. Okay, T01, T02, T03, and until T10. Okay, so you want to say, you want to ask the machine to use tool number 2, for example. So you have to write T02 M06. So the machine will write this instruction and will change the tool to tool number 2. Okay. So feed selection and input. So this is a feed rate. Okay, feed rate. For example, F100. Okay. Spindle speed selection. So we have similarly spindle speed in RPM. S1000 means we use 1000 RPM. Okay. So you don't need to insert the unit. You just insert the numbers. Okay, the unit will be in RPM and others. We will go through one by one. Okay, later. And the other M codes, the proprietary codes, other than machine, other than tooling moves. So we have M00 program stop, program end. So spindle, okay, the device that hold the tool, we call it spindle. Okay, spindle. So you want to ask the machine whether to rotate clockwise or counterclockwise. So use only one lah, either M03 or M04. So for example here, spindle speed selection, spindle speed selection, S1000, choose M03, M04 or M05. Don't write all, otherwise your machine pening nanti. So write for example S1000, M03, for example. Okay. So the machine will rotate at 1000 RPM, M03 S1000. 1000 RPM using a clockwise motion. So if you want to use counterclockwise motion, you should change M04 as 1000. Then before you stop everything, you have to spindle stop. Okay, you have to give the machine instruction to stop the spindle. Then M05. Okay, that's why when I show you the first slide, this one, so system shutdown, before the shutdown, it should tell the machine to stop the spindle, stop rotate the tool, okay, stop the spindle, then stop everything, stop the program. Okay, tool change, so tool change should follow with TXX. So if you want to coolant on M08, coolant off M09. So if you have clamping, clamping is used for hold your workpiece. So for example, you have workpiece. Okay. So clamp, you need to clamp it. Clamp. So there will be a clamping device to hold your workpiece. Okay. Clamp on or clamp off. Open or close lah. Program end means before everything, means end everything, end everything. Okay, like this, end everything. Program end. So machine will stop everything. And others, so I will let you know which one is important, which one is not, which one you need to remember, and which one you don't have to remember, because the quiz will be online, like test. I will give you 30 minutes or 40 minutes quiz, and you have to answer it. Okay, so the direction. Okay, last time we show you there is a positive and negative. So the rules is by using your right hand. So you have right hand fingers like this. Okay, like this. So you have X, Y, Z. Okay, X, your thumb, Y, and Z. Okay. So the one who goes out from these three fingers is positive. Very simple, right? And for another axis, for example, if you have more than 3 axis machine, you will use your again your right hand, okay, put it on the axis. For example, on the x-axis, okay, go up like this is positive. So if the axis go down, negative lah. All right. So this is an example of CAM software. Okay, CAM software. So this is the NC code. So imagine you have a design like this. Okay, you want to give instruction to the tools to grow from here to here, and again repeat in order to cut this. Okay, cut this impeller shape. So if you can see here, there are millions of coordinates point instruction. Okay, to the for the tools to cut this impeller. Okay, that's why we need this CAM software to help you to generate it automatically. So before that, you have to know lah. You have to learn how to generate the NC code for simple design. Okay. Then after you know what is happening, then you can use CAM software to help you lah. So all of this line, the green line, we call it as a tool path. Okay, tool path. Tool path. Okay, the path of the cutting tool. So they will go here, 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 here. So a lot of points, thousands, millions of points. So this is an example of CAM software, right? For example, here on the left, you know what cutting tool size that will be used, what pattern, and what strategies will be used. For example, 3 and 5 axis machining or 5 axis machining. Okay, I will show you some movement here if you can see it. So I can so this is your bulk material. Before you can get the impeller shape, so this is the initial shape of the impeller before it's being machined, right? So this has been fast forward and lajukan. So this is how the tool moves. Okay, this is how the tool moves according to the G code that already been developed by the machine, by the CAM software. So if you can see this tool, they are moving according to the coordinates that already made from the CAM software. Okay, you can verify lah whether it's good or not, all the paths. Okay. Then if you satisfied, you can use this setting, this what do you call it, tool path, and send it to the machine to cut it. Okay, for example, here, okay, so this is real machining. Send it to the machine. So we have 3 axes where you can see this one we call it spindle lah. Okay, so this one is the spindle. Okay, it hold the cutting tools. So this is the cutting tools. So if you can see here, it only move in 3 axis, X, Y, Z, bawah, right? 3 axis movement. Okay, there will be also 5 axis where you add another 2 axis. So the machine table will rotate and tilt. It will rotate, pushing, then tilt. Okay, for example, like this. So this movement, you need to use CAM lah. You cannot use what I call it manually because it's difficult, because all 5 axes move simultaneously. Okay, dia bergerak bersama-sama. X, Y, Z ni bergerak sama-sama. Imagine if you do it manually, maybe it will be accident will happen lah. Dia pun terlanggar dengan kita punya machine ni lah. Okay, I'll play it again. So you can see all 5 axes are moving together. Okay. So if you can see this blue hose is the coolant to cool down the process. Otherwise, it will be a lot of spark because high speed create heat and will worn out the tools. So we don't want that. So we give some fluid to lubricate it and to cool down. Okay, we have all these facilities in our lab, production lab. You can have a visit and let's see the machine. Okay, so far any question? Ada soalan tak? Okay, that is for the introduction. I need more time to teach you how to write the coding, but not today because we only have another 30 minutes. So I decide to show you. Before that, do you have any question about CAD/CAM? No, tak ada. So I will share the process of injection molding yesterday video. Ya, saya tuakan suara dia. Okay. Injection molding plastic processes. Okay, so enjoy the videos. If you have any questions, stop me and I can help you with your question.
To better understand the injection molding process requires understanding some properties inherent in plastic itself. The simplest definition of a plastic is any natural or synthetic polymer.
So this is called plastic resin. Okay, a hopper, this one, a hopper, this one is a plastic resin. Okay. So we need this as an input to a plastic injection molding machine.
That has a high molecular weight. There are two types of plastics, thermoplastic and thermosets. Thermoplastics undergo a reversible change from solid to liquid when heated and can be cooled and reground for reuse over and over again. Thermosets undergo a chemical reaction between two reagents when heated and achieve their strength through the interlocking chemical bonds. Once molded, thermosets cannot be resoftened. While thermosets are injection moldable, most materials used in injection molding machines are thermoplastics. Injection molding plastics is extremely complicated because of the infinitely changing pressure, temperature, and velocity inside the mold. These molding conditions directly affect the properties of each molded part. A change in any of the conditions will alter the parts produced. There are four primary elements that influence the plastic injection molding process: the molder, the material, the injection machine, and the mold. There are a variety of injection molding machines in use today. The vast majority of these machines are hydraulically actuated and have 3 platens. But newer styles, such as 2-platen injection molding machines and electric injection molding machines, are now gaining market acceptance. Injection molding machines range in size and complexity from desk-size units up to machines the size of a small house. Most injection molding machines are horizontally oriented, but vertically oriented molding machines are available. These vertical machines are primarily used for insert molding. All injection molding machines are a combination of 2 systems. an injection system, and a clamping system. The injection system heats the thermoplastic material to its appropriate viscosity or flowability and then forcefully injects it into the mold. There are two types of injection mechanisms: the reciprocating screw, which is the most common, and the two-stage screw. The main parts of the reciprocating screw injection system are the hopper, a reciprocating screw inside an externally heated injection barrel, a hydraulic motor, and an injection cylinder. Resin material is fed to the injection barrel from the hopper. These hoppers may be filled manually or vacuum-fed automatically, and often have dryers attached to the top to remove the moisture from the material. As the resin enters the injection barrel, it is driven forward by the rotation of the screw, which is powered by the hydraulic motor. The resin plasticizes or melts as the turning screw drags it towards the nozzle end. This is referred to as drag flow. Drag flow causes the polymer molecules to slide over each other, creating frictional heat, which melts the material. External heating bands provide additional heat to the injection barrel. The heating bands bring the material to its final temperature and compensate for the radiation heat loss. The temperature is controlled by 3 thermocouples in the barrel and 1 in the nozzle. Over time, many different mold designs have been developed that meet specific injection molding requirements. These mold designs include the Cold Runner 2-plate mold, the Cold Runner 3-plate mold, the Hot Runner mold, and the Insulated Runner mold. The Cold Runner 2-plate mold consists of 2 plates with the mold cavity and core mounted on them. The Cold Runner system molds the sprue, runners, and gate along with the parts. After ejection, the parts are separated and the rest reground. The Cold Runner 3-plate mold uses 3 plates to mold the part. These plates include the stripper plate, which contains the sprue, the middle or cavity plate, which holds the cavity, runner, and gate, and the movable plate, which holds the molded part. This type of Cold Runner mold design automatically separates the runner system from the part as the mold opens and is very easy to automate. The Hot Runner mold uses an electrically heated manifold that keeps the molten thermoplastic in the runners at the same temperature as the heating cylinder. The heated runner system is contained in a plate of its own and does not open during the molding cycle. Because of this, Hot Runner molds generate no runners or sprues. For this reason, Hot Runner molding, also known as runnerless molding, is fast and efficient. The Insulated Runner mold is much like the Hot Runner mold, but it uses a large diameter runner. During injection, the outer surface of the runner freezes. This insulates the center material, keeping it at the molding temperature.
Okay, that's all for injection molding. So we have another process, which is plastic blow molding. So how they make bottles.
Blow molding processes are the most popular methods used to produce hollow products out of thermoplastic materials. Blow molding evolved from the ancient art of glass blowing. Today, it is a leading plastic manufacturing process because of the wide range of plastic resins that can be blow molded and the many possible methods of blow molding. Blow molded parts range in size from the very small to extremely large parts. Bottles and containers are the most common blow molded products, but other items such as highway barrels, automotive components, double-walled cases, toys, medical items, and structural panels are produced. Blow molded products are formed from thermoplastic resins such as high-density polyethylene, medium and low-density polyethylene, polyethylene terephthalate, polypropylene, polyvinyl chloride, thermoplastic elastomers, polystyrene, polycarbonate, fluoropolymers, polyimide, and many other materials. Most thermoplastic blow-molded products are produced via extrusion blow molding using high-density polyethylene or HDPE. But there are many additional blow molding processes which include injection blow molding, biaxial stretch blow molding, and co-extrusion blow molding. These blow molding processes all use elements of either extrusion or injection molding or a combination of the two. In addition, these blow molding processes all share 4 common stages: plasticizing or melting the resin, Parison production when referring to most blow molding operations, or preform production when referring to biaxial stretch blow molding, Parison or preform inflation and cooling in the blow mold, and ejection from the blow mold. A 5th stage is necessary in extrusion blow molding for trimming and finishing the product. For the most part, blow molding processes all use the same blowing technique, whether it be through a blow pin, a needle, a stuffer, or core rod. It is in the production of the parison, or the preform, where these processes differ. The process of extrusion blow molding involves applying heat and pressure to thermoplastic resin to produce what is called the melt. This melt is then forced through a die to produce a parison, which is then dropped, trapped, or conveyed to an open blow mold for subsequent blow molding. Extrusion blow molding uses either an intermittent or continuous method for the formation of the molten parison. Intermittent extrusion produces a parison only when the blow mold is ready. These parisons are produced by using either a reciprocating screw or an accumulator and ram-style machine. Injection blow molding incorporates elements of conventional thermoplastic injection molding with blow molding and is generally more economical than extrusion blow molding for containers under a quarter liter in size and large production runs. Injection blow molding machines typically contain 3 stations: the injection station, the blow station, and the strip or eject station. The injection station is basically an injection molding machine. A ram, usually a reciprocating screw, forces the melted thermoplastic resin under pressure onto a metal core rod held within a closed, split parison cavity injection mold. After the outside skin of the parison has set, the parison mold opens, and the core rod carrying the parison rotates to the blow station. Once the core rod is in position, the blow mold closes. A trigger bar opens the core rod air passage. The air lifts the parison from the core rod except where it is held at the neck and expands it to the shape defined by the blow mold cavity. Once the part has cooled sufficiently, the blow mold opens and the part is indexed to the next station for stripping or ejection.
Okay, that's the difference between blow molding and conventional injection molding. So they have parison, they call it parison, where the air are pressurized into the what do you call it, the plastic to blow it. So the blow molding, they have a parison, they call it. Okay, I think that's all for today. Is there any question before we